Welcome to another Advent of Code walkthrough video. Today we're looking at 2022 day 15. So, our distress signal has led us down to some subterranean tunnels. We don't have time to search them all, but we have a bunch of deployable sensors. The sensors aren't powerful, but our device tells us that we're close enough to the source of the distress signal. So we take out the sensor system, hit the button, and they go down into the tunnels. Once they find a spot they'll think they'll give a good reading, they'll attach themselves to hard surfaces and look for the nearest signal source beacon. These sensors and beacons always exist at integer coordinates on a 2D grid. Each sensor knows precisely its own position and the position of a beacon, but they can only lock onto one beacon, and it will be the closest one to the sensor. And this is measured by Manhattan distance, which is the sum of the distances along each axis. It's called Manhattan distance because the city of Manhattan is organized like a grid. So the shortest path from one intersection to another is just the number of roads between and the number of streets between and the number of avenues between. Obviously because you can't drive diagonally through one of these blocks. And you'll never have ties with the beacon's distance to sensors. So then our sensors report back their own positions and the closest beacon for each one. So that's our test input. Let's grab our primary input. Okay. So this is a graphical representation of the test data. This isn't necessarily a map of all of the beacons though, because each sensor can only see the closest beacon. If a sensor sees a beacon, then you know that there are no other beacons that have distance closer than or equal to that one. So for example, if we look at the beacon at position 87 and its beacon at position 210, then this entire diamond of pound signs represents the area in which another beacon cannot reside. There could still be beacons outside of this diamond, just not ones that are closer than or equal to the closest one. So the problem here is that none of the detected beacons are actually producing the distress signal, so we need to deduce where the actual distress beacon is by finding where it isn't. So for now, let's keep things simple. We'll just count along a single row and figure out how many positions the beacon cannot be in along this row. So let's suppose that we have an arrangement of beacons like in the test data. Just looking at y equals 10, these hashes represent all of the positions in which a beacon cannot lie. So in this example with row y equals 10, there are 26 positions. Note that this b here doesn't count as one of these positions. We shouldn't count existing beacons as positions in which beacons cannot be present. Okay, so in the actual problem for the actual data, we'll need to change the row to 2 million. So first we need to parse the input. This input format is slightly annoying because it contains a bunch of extra random words. We only care about these numbers though, so we're going to use a regular expression to parse them out. And the pattern is just going to be an optional minus sign followed by a sequence of digits. So now we can just do for a line in open 0, sensor x, sensor y, beacon x, beacon y is equal to map into over pattern.find all within the line. So this will find all integers within the line and parse them into numbers. So let's go over two ways of implementing this. The first way is the faster way, or the way that takes a bit less thinking. So it's the one I did live on the contest. However, I knew for a fact that it wouldn't really lead well into part 2, so I'll discuss the smarter solution in a bit. So we're just going to keep a track of a set of x coordinates that the beacon can't be in, and we're also going to keep track of all of the known beacons that are within the set, just to make sure that we aren't like double counting. So we'll set a variable y equal to 10 just for the test data. We'll leave it as a variable because we'll need to change it between the test and the actual data. So now, first we need to find the actual distance. So that would be the absolute distance between the sensor and the beacon along the x-axis plus the absolute difference along the y-axis. Now we need to compute the range of coordinates along the row y. So what is that asking? Well, we are looking for all xy such that the absolute difference sx minus x plus absolute difference sy minus y is less than or equal to d. So that would be the diamond that we're looking for. Of course, y is fixed at capital Y. So we're actually only looking for this, x coordinates like this. And so we can move this to the other side because it's already known. And we get this here. And so the boundary of this range is going to lie at the maximum and minimum values, which are when these two are equal. In other words, sx minus x should be equal to plus or minus d minus the absolute value of sy minus y. So we'll call that value O for offset. It's going to be d minus abs xy minus capital Y. Now, if O is negative, what that means is that the distance is smaller than the row difference. This means that all positions within this row are further away than the closest beacon to our sensor. In other words, this sensor beacon pair does not actually give us any information. So if O is less than 0, we skip it. We do not take the absolute value because that would cause bugs. So the not smart method is going to be to just loop through all of the indices within this range. So low x equals x minus O and high x equals x plus O. That should be sensor x. So this defines the boundary range in which no other beacons can be. So now we can just do for x in range from low x up to high x inclusive, cannot.add x. Now if this beacon is along this row, so if by equals capital Y, we also need to add its x value to the known set so that we do not end up counting it as an impossible position. So if now we just print out the length of cannot minus known, so the set difference. We take all impossible positions and remove the ones that already have beacons. And so if we run this on our test data, we get the expected answer of 26. So now let's change y up to 2 million and run this on our actual data. That's only supposed to be this. And you see we get our answer of 4919281, which is expected. The second part is, of course, finding said beacon. And so this was fairly obvious. It was kind of implied from this part that we're trying to work out where the distress beacon is, and also it's just a natural continuation of the problem's storyline. And so the smarter method here would be to make this actually fast, because you'll notice that when I run this, it takes a substantial amount of time. It takes over 1 second. So we can imagine that part 2 is going to be a lot slower. And so 1 second for this part is completely unacceptable. We want this to run basically instantly. And fortunately, we can do that. You'll notice we're doing a lot of range calls here. So instead of adding all of the values within the range to the set, what if we just stored them as intervals and then just did some math at the end to combine the intervals together? So what we're going to do is we're going to save up all of the intervals in which our value cannot lie, and then at the end we'll merge all of our intervals together. We'll also need to do a bit of a check with this just to make sure that we don't double count anything. So let's get rid of our cannot and known sets, and let's get rid of all the logic here. Everything else can stay. Now we have LXHX, and instead of doing the range call, we're going to keep a list of intervals. And we're going to append the range. And we're going to keep these intervals doubly inclusive, so the left and the right side are both included in the interval. So this interval tells us all of the points that cannot exist. So now we can't just directly add up the lengths of each interval because of the intersection. So we're going to deal with this intersection by merging overlapping intervals. And there's a very nice way we can do this if we first sort the intervals. So now the intervals are sorted first by x and then by y. Oh, sorry, not by x and y. First by the lower bound and now by the upper bound. So now we're going to merge them together. So we're going to make Q an array which is going to contain all of the non-overlapping intervals. So for low, high in each interval, first of all, if Q is empty, then we're just going to append this interval to Q because there's nothing else, so it can't overlap. And now we're going to check. So because we did everything in sorted order, then our current interval has the low value of our current interval is no smaller than the lower bound of the last interval. And so what we're going to do is we're going to look at the last unified interval that we found. So Q low, Q high equals the last element of Q. So to check for an intersection, all we need to see is just make sure that our current interval isn't completely above our last interval. So if our low value is greater than Q high, in other words, there's no overlap at all, then we can just skip. But actually, we can do slightly better and do +1 here. And the reason for that is because if Q high is right below low, then because our intervals are doubly inclusive, then Q high and low are both within our bounds. And so we can actually merge the intervals because they're touching. They're not overlapping, they're just barely touching, but that allows us to merge them. So if we cannot merge them, then we can just append our interval to Q directly. But otherwise, if we can merge them, so if they are touching or overlapping, then we're going to modify Q. So I'm actually going to make these lists so I can modify them since tuples are immutable. So we're actually going to set the high bound of Q. Because here's the thing. Essentially what we're trying to do is our new interval of the two combined is the lowest of the lows and the highest of the highs. But the lowest of the lows is going to be Q low. And the reason for that is because our intervals are sorted. So we just need to do Q high equals the maximum of Q high and high. And of course, modifying Q high won't work because we're actually trying to modify the second index of the last interval, like so. And so now if we print out our unified intervals, we get that. It's just one interval now. Before the interval collapsing like so, we had a bunch of intervals like this. And if we sort them all, you'll see that these two are slightly overlapping, these two are just barely overlapping, completely overlapping, these two are barely touching, and there's a gap. And these two are overlapping as well. So all of these combine into one interval. So the only last thing we need to check for is our known thing. And so we're going to do this in a slightly less smart way. My reasoning for this is as follows. The second part is going to ask us to find the missing beacon, right? So it doesn't matter if we mark known beacons as impossible positions. So what we're actually going to do now is go back to our old behavior of just putting everything into a set. So we're just going to do cannot equal set, and we're going to bring back our known set from before. The point of this was to just get the interval logic set up. So this is the same code as before, basically. And now if we bring it back up to 200 million, we get that. Which you'll notice is still a lot faster, even though we're expanding it into a range at the end anyway. So this should hopefully be fast enough to let us continue. And so let's move on to part 2. The device indicates that the distress signal is coming from a beacon close enough, and it isn't detected by any sensor. But we know we have bounds for the coordinates. The x and y cannot be outside of 0 and 4 million. So that's what our device is telling us. So to isolate the signal, we need to find its tuning frequency, which is the x coordinate times 4 million plus the y coordinate, which is really just converting the xy coordinates into base 4 million so that we can submit it to the problem as one number. In our test example, the search space is going to be smaller. the x and y coordinates are going to be up to 20 instead. So for this part, we're going to also add an extra, we're going to change capital Y. We don't need this anymore. We're not looking at just a specific row. We're going to instead have m equal to 20, which will basically be the search boundary. We also don't need known anymore, and we also don't need this logic anymore. What we're now going to do is take this entire section and put it into a while loop, a for loop to search each row. Now technically you could probably optimize this more, but searching each row should be fine. The slow part about our P1 solution was the whole set thing. And so just doing interval math, this should be nearly instantaneous for each row, and looping 4 million times is not that bad. The time lost from waiting for the program to complete is certainly much shorter than trying to find a smarter solution, at least for me. Okay, so one other thing we need to make sure we don't forget is that open 0 opens standard input and reads everything. So if we repeat this part, it's not going to work. So we're going to need to read out the input first. So we're just going to do lines equals list of open 0. So that'll just read out all of the lines at once, so we can loop through the list multiple times. So for capital Y in range m plus 1, we're just going to keep it as capital Y so everything else still works properly, and we'll indent all of that code. So now at the end, let's print out Q just to see what we're getting. Run this on the test data. Oh, bad file descriptor. Shoot, I forgot to change this to our stored list. This gives us our intervals, and I'll print out the row to follow. So this gives us all of our row numbers and then the intervals, and these intervals, remember that they mean what isn't allowed. So see here, the entire 0 to 20 range is blocked, same here, all the way down until here. At row 11, we have two intervals. One of them goes from -3 to 13, and one of them goes from 15 to 25. Within the 0 to 20 range, there is a gap at 14, which means that x equals 14 is possible when y equals 11, which gives us our one singular beacon, x equals 14, y equals 11. So how do we isolate for this? Well, we're essentially just going to do a smart linear search for it. So we're going to start the bound at 0, and then we're just going to go all the way from 0 up to 20. But each time we see an interval, if the interval doesn't cut us off, then we know that we're in the right position. If the interval does cut us off, we can skip to the end of the interval. So this doesn't take us 20 steps, it just takes us how many intervals there are. And because these intervals are in sorted order, because our combining step put them in sorted order, this linear sweep does work. So for x, x starts out equal to 0, and then we'll loop through each of the intervals. For low, high in Q, if x is less than low, then that means that none of the future intervals will intersect x, so we can print x capital Y and exit the program. Otherwise, we're going to do x equals high plus 1. Because we don't just want to increase x one at a time, since we are currently within an interval, then we can just jump to the end of it. And so high is the upper bound of this interval, so we'll do high plus 1 to jump right past it. And then we'll keep scanning. Note that because we merged all touching intervals, this actually technically means that we've already jumped outside of an interval, which we'll notice when we get to this step. But we also might have jumped past our search boundary. And so if x is greater than m, which is our search boundary, then we will break out of this loop. Because otherwise we could potentially run into bugs where we find a valid index, but it's completely outside of our search range. And so now if we run this, we get 1411, our x and y coordinates. So we'll just take x multiplied by 4 million and add y. And that gives us our correct output. So now we'll just change the search range up to 4 million and leave this to run for a bit. It'll take a while because searching through 4 million rows still does take some time, even if searching each row isn't particularly slow. In fact, if each row just took 1 millisecond, then 1,000 rows takes 1 full second. So 4 million rows would take 4,000 seconds, which is quite a bit of time. This fortunately won't take that long though. The scan method for each row is a bit faster than 1 millisecond. In the meantime, how about I talk about the bug that I ran into? So the bug I ran into, well, the interval calculation method I did live was not nearly this smart. I had the intervals storing what was allowed, so the intervals started off as 0 up to m, and then each time I would do some math to subtract intervals, which for the record is a lot more annoying. But the problem was, as soon as I found an isolated coordinate that worked, I exited the loop. The problem is this was detecting a bunch of false positives, because I wasn't accounting for the fact that just because I have one isolated value doesn't mean that it won't be invalidated by a future scanner. So if I just unindented this code and checked the intervals for a unique value after all of the scanners were done, I could have probably placed within top 10. How is this still not done yet? It was not taking nearly this long when I was doing it on my previous code. Is there a bug in this code? Why do I get the feeling that there's a bug? Here's another bonus tip. Whenever you're not sure if your code is just slow or running into bugs, something you can do is add a print statement. So you can print y. The thing is, if you just print y, this will actually cause your program to slow down a lot because printing is slow. So we're going to do, if y is a multiple of 100,000, we'll print out y, just so we can get a little progress report. It's meant to be equals 0. Yeah, this is a lot slower than it should be. It ran way faster than this when I did it. So there's probably a bug in the logic that's causing it to take a lot longer to scan. Let's see what's up. Okay, so while I was investigating, the program actually did finish. It took a total of 209 seconds, which is 3.5 minutes, which is a bit unacceptably slow in my opinion. I did figure out one issue, which is that setting x to high plus 1 isn't probably a good idea. Because if you have a negative interval, like let's say -1 billion, -1 billion, then x is not less than that, but we'll move x backwards. So we don't want to ever move x backwards. So x is going to be the max of x and high plus 1. And I think this should speed it up a bit. It actually does not. That's very weird. Oh, yeah, right. regex is slow. You shouldn't be doing parsing steps repetitively like this. That's my bad. Yeah, so we can actually do this. So it'll be list map int pattern dot find all line for line in open 0. Yeah, so now we can just do for sx, sy, bx, by in lines. Yeah, my mistake. Never do parsing steps within a loop. This should speed it up significantly. Yeah, there we go. That's a much better speed. Yeah, so the reason for this is just because, let me get rid of that annoying print line. Regex is quite an expensive operation in terms of time, And because the data isn't ever changing and we're just looping through the same intervals each time, we actually should probably be, sorry, the rest of this can't be packaged beforehand, but we definitely should be doing our parsing just once at the beginning. So let's just let this run for a while and see how long it takes. Okay, yeah, so this took under 40 seconds. That's a lot better time. Okay, so yeah, I think the important takeaway for this one is the interval math, because there have been many problems like this, and this interval method is the easiest I can think of. So if you have to calculate a bunch of intervals, never use sets, because it's always going to be way too slow unless it's like day 5 or earlier. You can store the list of intervals and just add them all out at the same time, and then sort them, and then just go through them using this loop here. We will keep a modified list that contains the unified or like conjoined intervals, basically the minimal set of intervals that covers the same values. Since they're in sorted order, we can traverse them in sorted order. Of course, we need to add the first interval to Q directly, and then otherwise, if we can't overlap the intervals, then none of the future intervals can overlap with our current one anyway, because of the sorted order. And so we can just append it and continue. And otherwise, if the intervals are touching or overlapping, we can just stretch the first interval up until the second interval, assuming the second interval it does go further than the first one. And also, when trying to search for a spot that isn't contained within intervals, which probably has shown up at least twice within AOC before, you can just run a linear sweep, but instead of increasing x by 1 each time, we just jump to the end of the interval each time. And in fact, we could do a bit more optimizing by skipping any intervals that are fully negative, but I can't really be bothered to do that. So that's all for this video. Thank you for watching. I hope you enjoyed and learned something, and I'll see you tomorrow for day 16.